This is Dr. Holt. This video is AP Physics C, Angular Momentum, the Nature of Vectors. When we calculate torque, we want to note that torque is always going to be the cross product of R cross product F. So if I'm trying to find out what the torque is around a certain point, I'm going to take this R vector, I'm going to cross product into the F vector. So to do that, I would take this distance here, this R vector here, I would cross product into the F sine of theta, because when I do the cross product, again, I can only do the cross product of perpendicular components. So the R cross product F would be the same thing as multiplying R times F sine of theta, and that would give you a vector quantity of torque along the z-axis. When we look at angular momentum is defined as R cross product P, where P is the linear momentum. Here I have a mass of m traveling at this distance, some distance from a rotational point, and I want to find out what the angular momentum is. At the very instant it passes, I'm going to do the cross product of R cross product P, or R cross product mass times velocity, and again, these are both vector quantities. When I do that, and using the right-hand rule, the vector itself would be along the z-axis. So the angular momentum would be around this z-axis, and is defined again as R cross product P. Always remember, with the right-hand rule, you can slide your fingers along the A value and then bend your fingers back toward B. The direction your thumb points is the resultant vector. So in this case, A cross product B, my fingers extend along the A line or A axis. I rotate them back toward B. When I do, my thumb points up, so that would give me my resultant vector. Note that you can solve these vectors if you want to, or the cross products, using determinants. Let's say, for example, that I have an R vector that's defined as, let's say, 0 I hat plus 3 j hat minus 6 k hat. And I have a force of 2 I hat minus 4 j hat plus 2 k hat. And again, I want to do the cross product here. I want to do R cross product F, because let's say I'm going to find out what the torque is going to be. To set that up, I would list my I hat first, my j, and my k. Okay, since we're doing R cross product F, I list the coefficients here. I'd have a 0, I'd have a 3, and I'd have a minus 6. For force, I'd have a 2, I'd have a minus 4, and I'd have a 2. So I want to do the determinant of that. To start out, I'd bring the I down. Now to do the I, just a good reminder, remember, this is the I value. You're going to multiply this times this. So give me 3 times 2, and then you're going to minus coming back down the other way. Again, I hope you remember this from your other math classes. And that'd give me minus 6 times minus 4. All right, now we get rid of that and get rid of that. Now remember, you're going to negate this one, so that'd be minus j hat. When I'm doing my j hat, another good way to think about this is I basically cancel this row out here and cancel this row out here. So now to do j hat, I do 0 times 2, this times this, minus negative 6 times 2. And now when it comes to my k value, the only thing I'm really going to do is just slide this over here, and to get the k hat, I do plus k hat of 0 times negative 4 minus 3 times 2. All right, again, this is a vector quantity, so let's see what the torque would be in this case. I'm going to get 3 times 2, that's going to be 6, minus negative 6 times 4. So negative 6 times 4, that's 24. That gives me minus 24 there. 6 minus 24, that gives me negative 18. So I'd get negative 18 I hat. Now I'd come to j hat. I'm going to negate that right now because I got a negative value here. I got 0 times 2 minus negative 6 times 2. Negative 6 times 2 is negative 12. I have a negative here that makes it plus 12, but I have a negative here, so that makes it minus 12 j hat plus k hat. I come over here, that gives me 0 minus 6. Okay, and that would be my answer using determinants to determine what my torque would be. And again, you can use that for angular momentum also. When we get into solid masses, now our equation for our angular momentum is going to change slightly. And we're going to be using I omega. So again, we're using this for more of a particle type of motion where you have an object that has mass that's traveling around an object. It's just a single mass. Then we can get away with doing RP. Now we could do this for an object that has a solid mass, but again, we'd have to do it billions and billions of times because each particle along here has different velocities because they're different distance away from the axis of rotation. So an easier way to do this is just use I omega. Now where I got that is I know that velocity is equal to omega times r. So I've converted omega times r and I move the r over and I get m times r squared. Now note mr squared by definition in previous lectures is going to be the moment of inertia. So that's where this equation comes from, that the angular momentum is equal to I times angular velocity. And again, that's going to be for objects that rotate around their own axis that have moments of inertia. The units for angular momentum is going to be kilograms times meters squared over seconds, or you convert that to Newton meters times seconds. Let's talk about the conservation of angular momentum. A rigid body will have a natural tendency to maintain a constant angular momentum. If the moment of inertia remains constant and then no external forces are applied to the system, then in all cases the angular momentum will remain constant. And a good example would be like our universe where there's no external forces being applied, we would have constant angular momentum. Or our Milky Way galaxy, or solar system, or the Earth rotating around the sun, if there's no external forces being applied, then in all cases the angular momentum will be constant throughout. Now if torque is being applied to the system, things will change because the torque acting on a particle is equal to the time rate of the change of the particle's angular momentum. So if a torque is being applied, then you will see a change in the angular momentum of that particular system. I'm going to work a few problems through here, and as far as good examples, the first question or first problem, I have a 2 kilogram mass is traveling along a horizontal, we'll call this in the I hat direction, and it's traveling 4.5 meters a second, and I want to find the angular momentum about this specific point. So in this case, I can go back and use the definition of angular momentum is equal to the R cross product P, the linear momentum. So to do the first one, my R value here would be, and I'm just going to list it, the only component would be 6, and I can make that negative j hat. When I do my p-value, I will get 2 kilograms times 4.5 meters per second. That's going to give me 9 kilograms meters per second. Again, that's going to be I hat. Now, if I do the angular momentum, again, it's going to be R cross product into P. Again, you cannot reverse these. If you do, you're going to get your vector going in the opposite direction. So when I do that, I will get -6 meters J hat crossed into 9 kilograms meters per second I hat. And when I do that, that's going to give me 54 kilograms meters squared over seconds. And that's going to be K hat. Now you may ask yourself, why didn't I get a negative? Well, I can prove that by doing a determinant, or you can do right-hand rule. If you did right-hand rule, your fingers go down this way and you wrap your hand back that way, your thumb will be coming out of the screen and they could see it's a positive. However, you can do that with a determinant fairly quickly. And again, I probably would not recommend it for these type of cases. I'd just go right to the right-hand rule. Just saves time, but we can prove it. Again, I put the R value in first. I have 0, I have -6, I have 0. On the P, I only have a 9 here, I have 0, and I have 0 here. Again, if I'm going to do the determinant of that, I'll start with the I hat. When I do I hat, I get -6 times 0 minus 0 times 0. That's going to give me a 0 there. And again, remember, you have to negate the J hat. When I do J hat, I get 0 times 0 minus 0 times 9. That also gives me 0. And I do plus K hat. And when I do the K hat, I get 0 times 0 minus -6 times 9, and that gives me the 54. And that's why I'm getting a positive 54 instead of a negative 54. All right, in problem number, this one here, again, this is going to be very similar. What's going to be the difference? Isn't the difference really going to be this? R, in this case, is going to be 6 meters J hat positive. And again, the p-value in this case is going to be 9 kilograms meters per second. And again, that's I hat there. Obviously, if we do that, in this case, we would get negative 54 kilograms meters squared over seconds. Again, that would be in the K hat. Again, I'm sure you can see why. Again, you can do right-hand rule. Fingers go up, rotate this way. Your thumb would be going into the screen. So they give you negative K. Again, if you're not comfortable with that, run it through a determinant and you'll see why you get negative. Okay, in the third case, here your rotation about this axis here. In this case, you would have your R value be -6 meters. But then look what you would get for your P value. You get positive 9. You can't cross an I into an I. So in this case, your angular momentum in this case would be 0. In this case here, I have an individual has a moment of inertia with the weights on each end at 5.33 kilograms meters squared, has an angular velocity of 3.74. There's no external torque being applied. He's going to pull these weights in. His moment of inertia is going to decrease. Since there's no external torque being applied, we can apply this. The initial angular momentum must equal to the final angular momentum. We will find out what our initial is. Our initial angular momentum is just going to equal to I times omega. So we would have 5.33 kilograms meters squared times 3.74 radians per second. All we have to do is set that equal to the moment inertia I have here, 1.60 kilograms meters squared. Solve for omega 2 or omega final, whatever you want to call it. If I run those numbers, I will find out quickly that omega final is going to equal to 12.46 radians per second. And that's why when we did demos in class, you notice that your angular velocity increased as you reduced your moment inertia. Again, it all comes back to this, the conservation of angular momentum. In this problem, I have a 21.2 kilogram child. It can be running at 4.10 meters per second toward the rim of a merry-go-round. A merry-go-round has a radius of 2 meters. We want to find what is the child's angular momentum with respect to the center of the merry-go-round. So we're trying to find out what it is about this point here. Okay, what you cannot do, and again, this is incorrect. In this particular problem, I cannot just say the angular momentum is equal to the radius, which would be 2 meters, times the mass of the child, which in this case was what, 21.2 kilograms. Times the child's velocity of 4.10 meter per second. Okay, I cannot do that. The reason I cannot do that, remember that angular momentum is a cross product of r crossed f. Okay, so this is incorrect. You cannot do this. To do this problem, there's two ways you can do this. You can either find out what the radius is right here. I could find out what that is as long as that is a perpendicular point right there. Then I could take the mass of the child times velocity and then take this r distance, multiply it by the mass times velocity, and I could find the angular momentum. That's one way to do it. The way I'd recommend you do this is to find the components of this. So let me erase this real quick. So to do that, this child has two velocities. I have a velocity going this way. Sorry, not I. The child has a velocity going this way, and the child has a velocity going back this way. Now, this happens to be 135 degrees, so the angle here will be 45 degrees. Here, because again, that's 90 degrees. So to find this component here, all I'd have to do is to take 4.10 meters per second, multiply it by the cosine of 45 degrees. To find this one here, I would take 4.10 meters per second and multiply that by the sine of 45. Again, obviously, the sine of 45 and the cosine of 45 are the same. So to find that, to find the angular momentum at this point, L, it will take my r value, the radius, and the radius was given as 2 meters. I will multiply it by the child's mass, 21.2 kilograms, times the vertical velocity, in this case it would be 4.10 meter per second, times the cosine of 45 degrees. When I do that, I believe I get 123, approximately, I'm rounding a little bit, 123 kilograms meters squared per second. Now, if that child has that much angular momentum, if the child jumps onto the merry-go-round, then I could very quickly find out what the angular velocity of the merry-go-round would be by going back and saying that L initial must equal to L final, which in this case would equal to angular velocity times the moment inertia. So if the child's sitting out here, I could find the find the moment inertia of the merry-go-round with a child out here at the outer edge, and then I could find this value here by setting all this equal to 123 kilograms meters squared per second. Okay, another problem. Here I have a frisbee. I'll work through this one. I want to find the angular momentum of a 0.13 kilogram frisbee. It's a uniform disc, a radius 7.5 centimeters, spinning with an angular speed of 1.15 radians per second, and then a 95 kilogram person running with a speed of 5.1 meters per second on a circular track of radius 25 meters. To do the first part, I will go back, and I know L is equal to I omega. Again, those are vector quantities. Okay, we have a uniform disk, so I will use a moment of inertia is equal to 1/2 the mass of the disk times radius squared. I will run that value. That's going to give me 1/2 times the mass of 0.13 kilograms times the radius, and that's 7.5 centimeters, so that's going to be 0.075 meters squared. I will run that value, and that will give me 3.66 times 10 to the minus 4th kilograms meters squared. Okay, that's my moment of inertia. So then I can go back and say that the angular acceleration is going to equal to 3.66 times 10 to the minus 4th kilograms meters squared. I will multiply that by the angular velocity of 1.15 radians per second. And when I do that, I will get a value of 4.2 times 10 to the minus 4th kilograms meters squared per second. All right, the second one, I have a 95 kilogram person running with a speed of 5.1 meters a second on a circular track radius 25 meters. Just draw a quick circle here. Get rid of this. This will be my person running around the track. I will give that velocity of 5.1 meters per second. Okay, it's a 95 kilogram person. All right, could I not just then say that L is equal to R cross P, or my linear velocity, or linear momentum? The radius here is going to be 25 meters. So I take 25 meters, multiply it by the mass of the person, 95 kilograms, times the velocity of 5.1 meters per second. And in this case, I will get a value of 12,000 kilograms meters squared per second. Now, again, it depends on where you have the person, whether you want to let that be positive or negative. I'm just going to give it this with you, the actual magnitude. It's up to you to decide whether you want it to be positive or negative. All right, going to keep moving on. Again, I'm doing quite a few problems, but I want to make sure you understand and have some good experience with these. In this problem here, I want to find the angular momentum of the Earth as it rotates on its axis. We have the mass of the Earth given as 5.98 times 10 to the 24th kilograms. The radius is 6.37 times 10 to the 6th. Okay, again, we treat this as a sphere, and the moment inertia of a sphere is going to be 2/5 mr squared. So first thing I want to do is I want to find out what the angular velocity would be. Angular velocity, we want to get that in radians per second. I know I do 1 revolution in 24 hours. Okay, I know there's 2 pi radians in 1 revolution. So revolutions there cancel here and here. Now I'm in hours. I want to go to seconds. Hours in my denominator, I'll put 1 hour up here. There's 3,600 seconds. Hours cancel here and here. Again, I'm going to get my units in radians per second. I run that number there, and I would get a value of 7.27 times 10 to the minus 5 radians per second. I will go back now and just use L is equal to I times angular velocity. I put my moment inertia as 2/5. Again, I get the mass of the Earth, 5.98 times 10 to the 24th kilograms, times a radius of 6.37 times 10 to the 6th meters. We will square that. I will multiply that times omega, which we said was 7.27 times 10 to the minus 5 radians per second. And that will give me an L value of approximately 7.06 times 10 to the 33. Again, that's going to give me units in kilograms, meters squared over seconds. All right, I have a few more problems I was going to work, but again, I don't want to make this video too long. I'm going to skip through a couple of these. I want to get back to this point here, and I want you to note that torque, again, we know from previous lectures, is going to be I times alpha, the moment inertia times angular acceleration. But torque is also, if there's a torque is being applied, it's going to give me the change in angular momentum over change in time. So again, if there's an external torque being applied, then the angular momentum is not conserved. There will be a change in angular momentum. Just a simple problem here. I have a light wind. In a light wind, the windmill experiences a constant torque of 255 Newton meters. If the windmill is initially at rest, what is the angular momentum after 2 seconds? I just go back to torque is change in angular momentum divided by time. So I find out what the change in angular momentum is by bringing the time up to here. I got my torque of 255 Newton meters. I multiply that by my seconds, and that's going to give me a change of angular momentum of 510 kilograms meters squared per second. All right, again, this is more of an introductory type of a lesson on how to do the conservation of angular momentum and to know that torque results in a change of angular momentum in respect to time. Again, work through these problems carefully. Be meticulous about the way you do it. You should be in great shape to do these problems. As always, I wish you the best of luck with these physics problems.